Hi and welcome. In this video, we will go through the following topics. First, I will show you how to build a speedometer for a spacecraft, and I will try to prove why speed is not relative but absolute. There is a universal static reference frame where velocity equals to 0. Then I will explain why Michelson-Morley experiment can only give us a negative result. After that, I will propose a hypothesis to explain the mechanism of Lorentz contraction and time dilation. So let's begin. We all know light speed is constant in any circumstance. According to current theory, if a boy Alex stood at the center of the train, he then emitted two lights into opposite directions. No matter if the train is moving or not, he will observe the lights will reach both walls at the same time. Meanwhile, there's another boy, Bob, standing outside the train watching Alex's experiment. Since Alex's train is moving towards right, Bob will see the light heading to left hit the wall first. It's because the left wall was moving to the light whereas the right wall was escaping from the light. When light speed keeps constant, it will be the result. This observation difference between Alex and Bob is a classic example to introduce theory of relativity. Now Alex has decided to change his experiment setup to a laser ring. Let's see what will happen with wave perspective. In Alex's observation, the lights start from the center of the train, hit both walls at the same time, travel back to the center, and meet again simultaneously. Since light speed is constant, everything is nice and in harmony. Now it's Bob's turn. He will see the light heading left hit the wall first as the wall is moving to right. When the lights reflect, the situation will reverse. The left light will need more time to reach the center since the train is moving right escaping from the light. But since both lights travel the same distance, they will finally meet again at the center simultaneously. As you might already realize, from Bob's perspective, since he sees the light sources moving, he will observe redshift and blueshift effects. Is it another trick due to relativity, or is it a real contradiction? To figure it out, Alex makes a small modification to his setup. Alex adds an interferometer to the setup that can slide horizontally within a finite length d. Alex would like to count the fringe to verify if there's any shifting. If redshift or blueshift exists, the number of fringes being counted when sliding the interferometer should be more than no shifting exists. According to current theory, from Alex's perspective, Alex should not be able to observe any speed differences for both lights. Let us assume the number of fringes Alex counted is x. But from Bob's perspective, since the train is moving, one wall is approaching the light source while another wall is escaping from the light source. There should be redshift and blueshift effects. Therefore, when Alex slides the interferometer, the number of fringes counted at Bob's side should be more than x. Here comes the question. Whose number should be correct? My answer is, according to Haffel-Keating experiment results, in this case neither Alex nor Bob is the correct static reference frame. We should use the center of Earth as the static reference frame instead. In Haffel-Keating experiment, we found that the clock on the plane flying to the east runs slower than the clock on Earth's surface, and both clocks run slower than the clock on the plane flying to the west. Because when you use center of Earth as the static reference frame, all three parties are in motion, whereas the plane flying to west moves the slowest, thus having the smallest time dilation and the fastest clock. This means we cannot simply take any point as static reference frame. The nature knows where the static reference frame is and knows how fast each object is moving. In Alex and Bob's case, we at least need to take Earth's center as a static reference frame to get the correct results. If the train is moving from west to east, Alex should be moving faster than Bob. Thus, the number of fringes observed by Alex should be more than those observed by Bob. If the train is moving from east to west, due to Earth's rotation, Bob should be moving faster than Alex. In this case, the number of fringes observed by Alex should be less than those observed by Bob. Since both Alex and Bob are moving, redshift and blueshift effects should be able to be observed from both perspectives. As long as the train is moving, Bob's fringe count cannot be equal to x. And by this experiment setup, Alex should be able to measure the train's speed without reference to external parties. He can just calculate his current speed from the difference between observed fringe count and static fringe count. It's how you can make a speedometer for the spaceship. Indeed, with this setup, you will find even the center of Earth is not the static reference frame. Since the Earth is circulating around the Sun, and the Sun is circulating in our galaxy, and our galaxy itself is also in some sort of motion. Through this experiment, you will identify the real unique static reference frame, a zero-velocity reference. In other words, I am saying speed is not relative, since it violates Haffel-Keating experiment observations. And in fact, speed is absolute, can explain other phenomena such as the negative results of Michelson-Morley experiment, Lorentz contraction, and time dilation. And we will go through them later in this video. As you might already realize, by counting the number of fringes you can only determine the speed at specific axis. You don't know the moving direction yet. To determine the moving direction, you can measure the difference between before and after the acceleration. And with measurements in all XYZ axis, you will get the accurate velocity in the 3D space. This is the complete theory to determine your current speed using the characteristics of constant light speed. Being able to measure the velocity has many practical usages. For example, after knowing the Earth's velocity in space, you can subtract it by your own velocity to get your geolocation without the GPS satellites. Since the Earth is rotating, every point on the Earth should have a different velocity. You can also get a more accurate age of different galaxies in space. The one we observed with the largest redshift might not be the oldest galaxy. It might be just because it's moving in opposite direction to our Earth. The Michelson-Morley experiment was an attempt to measure the motion of the Earth relative to the luminiferous ether. I assume you all know this experiment very well. To save time, I'm not going to introduce it here. I will just describe what's happening in the experiment setup if speed is absolute but not relative. Here is a radar speed gun. We first assume the environment is not moving. The radar emits an electromagnetic wave to the target. When the wave bounces back and hits the receiver, it checks if redshift or blue shift exists to determine target speed. If both parties are static, you will see the wave coming back without distortion. If the target is moving towards the radar, since light speed is constant, the reflecting source will create a blue shift effect on the reflecting wave. The radar can then calculate target speed by comparing it with the emitted wave. If the target is moving away from the radar, since light speed is constant, the reflecting source will create a redshift effect on the reflecting wave. The radar can then determine the target speed by identifying the redshift effect. As we know from the spacecraft speedometer that speed should be absolute, let's see how the waves look if the environment is moving. Assume the environment resultant velocity is v towards right. Consider both parties have relative motion equals 0. When the wave was emitted from the radar, since the radar is moving right with speed v, there will be a redshift on the wave. But interestingly, when the wave reaches the target, since the target is also moving right with speed v, the redshift would be cancelled out. That means, from the target perspective, the wave frequency received is the same as the wave frequency emitted from the radar. Now the wave is reflected back to the radar. Since the target is moving right with speed v, the reflected wave would attain a blue shift. Since the radar is also moving right with speed v, when the blue shifted wave reaches the receiver, it will be read as no distortion at all. As you can see, the redshift and blue shift effects induced due to environment movement will be cancelled out by the walls. Although the time needed for the wave to travel to and from the target is different, when we are focusing at the walls, we won't notice the distorted wave during transmission. Therefore, although speed is absolute and time needed for lights to travel across each arm is different, the Michelson-Morley experiment setup will still only give us negative results. Lorentz contraction, or length contraction, is the phenomenon that when an object moves, it will be measured to be shorter in the moving direction. It was postulated to explain the negative outcome of the Michelson-Morley experiment. In the Michelson-Morley experiment, we found that no matter how we rotate the setup, we could only observe a negative result, implying a shorten on the arm in the moving direction. Consider the case where the setup is moving right. When the upper arm and the right arm are equal in length, the light travels at the right arm will need to travel a longer distance back to the center when compared to the light travels at the upper arm. If we rotate the setup, an observer should be able to see a positive result in the Michelson-Morley experiment, since the two lights will now be out of phase. But in reality, we could only observe a negative outcome. In order to explain this, the length contraction hypothesis came out. When an object has a velocity, it will contract in the direction of movement. Therefore, the lights that travel in the upper arm or right arm will not be affected by the background speed and will be traveling the same amount of time no matter how the setup rotates, giving us the negative outcome. I'll now show you my hypothesis to explain why this happens. Below is a simple atom model. At the center is the nucleus. Outside is an electron cloud. Assuming electron speed cannot exceed speed of light, when the atom is moving in left or right, the time needed for an electron to travel left and right should be more than the time needed to travel up and down. If the probability of finding an electron is the same throughout the electron cloud, contraction on the cloud will be a must. And this atom-level contraction is the truth behind Lorentz contraction. Well, since speed is absolute, Lorentz contraction will not be relative. Only the object in motion will experience length contraction. Faster the speed, more the contraction. The Carteret paradox doesn't exist. Here's an atom. Imagine if you were able to stop the electron movement. Would the atom able to involve in a chemical reaction or able to conduct electricity? If you were able to stop all force carriers' movement in the atom, will different forces still be able to transfer properly? My answer is no. The atom will behave like its time is stopped. Since the speed of all elementary particles are limited by speed of light, as we already saw in the Michelson-Morley experiment, the distance needed for an elementary particle to travel from point A to point B within an atom will be larger on a moving atom than a static atom. And since they need more time to travel, all the physical and chemical activities performed at an atom will require more time to complete, in other words, become slower. That's the story behind time dilation, and that's why when an object moves faster, it will experience greater time dilation, because all those elementary particles will travel a longer distance. It also applies to the case of gravity. Since the space-time was curved, the elementary elements will need to travel farther. The two situations are indeed the two sides of the same coin. And if we were able to accelerate an atom infinitely so that it can exceed light of speed, its time will not reverse, as time doesn't work that way. Our measurable time is just the rate of chemical and physical activities we observe from an object. There's no grandfather paradox. In this video, I have tried to prove speed is absolute but not relative and show you how you can build a speedometer to verify it. I have explained how speed is absolute, aligned with the negative outcome of Michelson-Morley experiment. I have proposed my hypothesis to explain Lorentz contraction and time dilation. It's the end of this video. Thank you for watching.